Okay, so let's go on. So just now I just saying that so when we try to solve a constant coefficient ODE, we have 3 steps. This is very important, so I repeat again. So the first step is to solve the homogeneous solution, and then the second step is to solve for the particular solution, and then the first step is to find the complete solution by adding them together. So the homogeneous solution means here is the original. This is the original function differential equation we would like to solve. So the first step is to make the right side to be 0. So we just remove this one. So the right side becomes 0. And then when we try to solve for it, which means that so this x of c should satisfy this one. And then we will try to solve for the particular solution, which means that this particular solution is related to this function g of t. And then we try to add them together to form the complete solution. So which means that if we try to apply the property of linear, which means that for the first step when we try to solve a homogeneous solution, which means that x of c, so let's say we can still call the original function, call the original differential equation like f of x t, and then of course with this derivative, but I don't write it explicitly. So this is the original differential equation. So on the left side is a function of the x of t, and then the right side is a function of time, function of the independent variable. Okay, so the first step we will try to solve for the complementary solution, and it should satisfy this one, f of x of t equals 0. So the first step we make the right hand side to be 0 and then solve for it, which means that it satisfies this one, which means that we should have f of xc of t should be equal to 0. So we should have this formula. Okay, and then for the second one, xp of t are the particular solution which is related to this one. In this sense, we should have f for the particular one, for the particular solution xp of t. It should satisfy f of xp of t equals g of t, equals the xp of t should satisfy the original differential equation. Okay, you may consider, okay, why not this one is sufficient? Why not this one is sufficient? The idea is that if maybe there are many functions that satisfy the first one, and it is equal to 0 to the right hand side, and here as much as we have linear condition, or at least for this one we have maybe actually we should need linear. So which means that if we have f of xc of t and then plus f of xp of t, it should be something like this is 0 and then plus g of t. So on the right side is g of t, no problem. And then as much as we have linear, so if it is linear, it should be something like f of xc of t plus xp of t. Okay, so this will be the complete solution, because if for some of the function which makes the function to be 0, then if we just add it to the particular solution, it does not influence the output value, then all the function should satisfy the original function equation. So the idea is like this. That's why we need to solve for the homogeneous solution first, and then the particular solution, and finally we get the complete solution for the differential equation. Okay, so first of all, we will try to solve for the homogeneous solution. So which means that we try to make the right hand side to be 0. Here we have g of t, which we just let it to be 0. I do not mean g of t is 0. Here it only means that we change this g of t to be 0, and then we try to solve for this one. Okay, so actually it can be an nth order equation, but here we only show the case for n to be 2. If n to be 1, it is even more simple, so it is easy to understand. And if it is more than 2, the idea is that, if it is more than 2, or maybe when you consider the conclusion, so you can see if it is a second order constant coefficient ODE, so we will convert it into a second order algebraic equation with one unknown. So actually I think in high school you should know what is the solution to this algebraic second order equation. Okay, so if it is more than 2, more than second order, then still you can find the solution, but not that. Maybe not that. Maybe you need some factorization or whatever. So I think second order is enough. At least in the exam you need to calculate for second order, but for more than 3 order. Even in high school you seldom calculate the equation with more than 3 order unless it is easy to factor. Okay, so here we just use an example of a second order constant coefficient ODE. So here we, rather than write it as a2, a1 and a0, we write it as a, b, and c, like this. So a times the second derivative of x plus b times the first derivative of x plus c times the original function x equals 0. Okay, so here we try to find which type of function satisfy this functional equation. So of course, if nobody tells you, you might try different types of function to see which function satisfy. So here we tell you that we can try this this exponential function. Exponential function is a good choice. Why? Because when we have e to the x, if you just take the derivative, it turns out to be itself. So this is a good thing. For derivative. So here we try to use the exponential function. And of course it is not a function of x here, it's a function of time. So maybe e to the t. But e to the t turns out to be e to the t, then maybe it does not really help. So we try to put a constant unknown value there and then see which value help us. So here, if we have exponential to s of t, so here if we have exponential to s of t and then we take the derivative with respect to time, it of course has exponential to s of t. It still have this one, but due to the chain rule, we should take the derivative to the exponent. So take the derivative of st with respect to time, we have an s here. So if we take second derivative, we have s squared in the front, so on and so forth. So this is the idea here. So if we try to assume x of t to be this function and then plug it in, then we will have a second derivative. So we have s squared here and then multiply the original function and then plus b, and then first derivative. So we have s and then exponential to s of t, and then c times x, c times exponential to s of t. Okay, and then equals 0. And then of course we have exponential, the same term up here. So we can factor out and then we can divide it because exponential to s of t is never 0. So we can divide it. If it is 0, it may be 0, then we need to consider it individually. But exponential function is a function gives you positive value if the domain is real number. So we can be very safe to just derive this term out. Okay, so in this sense, the remaining is as squared plus bs plus c equals 0. So it turns out to be a second order algebraic equation, so which is easy to solve. So in high school, you know the solution to this one should be minus b plus or minus square root of b squared minus 4ac all over 2a. Okay, so this is the solution. I hope you still remember that. So, and actually, when we talk about the differential equation, or sometimes for the matrix, when we try to calculate for the eigenvalue for a matrix, okay, we will call this one auxiliary equation, or we may call it characteristic equation. In Chinese, it's called 特征方程. Okay, characteristic equation. Okay, so the solution to this characteristic equation, sometimes called the characteristic value, or in linear algebra it may be called eigenvalues. Okay, so and these values are important to us because if here we try to assume this is the function to satisfy the so-called homogeneous solution, because original with a g of t is the ordinary differential equation we would like to solve, and if we try to make the right hand side to 0, this one is called the homogeneous equation. So this is the homogeneous equation, and then here we try to assume this is a function to be the solution of the homogeneous solution. Then finally we know that S should satisfy this characteristic equation. So which means that for this one is a second order algebraic equation, it should have a two solution. Okay, so which means that the two values satisfying this characteristic equation, and then we plug it back here, it should make the left hand side to be 0. Okay, so this is the idea. Okay, so here we have several cases, just like what we have learned in high school. So here what we know is that we have this homogeneous solution, and then we assume this is a solution. So, and then according to previous page, we can know that S should satisfy this algebraic equation, which has the same order as the homogeneous solution. Okay, so there will be 3 cases, just like what we have learned in high school, which means that this one, maybe this one, maybe you just, maybe you misunderstand. This is a minus sign. This is not a minus sign. So maybe I just remove it. Okay, so here there are 3 cases. If this is the delta to be b squared minus 4ac. If delta is larger than 0, we will have distinct real roots, because the solution is like negative b plus or minus square root of b squared minus 4ac, and then all over 2a. So the idea is that this term, whether it is a positive, 0, or negative, so it's positive, then both values are real number. So we have a distinct real roots. If b squared minus 4ac is 0, then this is 0, so plus or minus 0. So the two values are repeated real root,重根. And the third case is the most complicated one, which means that this one is negative, these terms are negative, which makes that we take the square root of a negative value, which becomes the imaginary number. So imaginary number is I to be negative, a square root of -1, or usually in our field in ECE or double E, we would use J rather than I, because we have the current. Usually the current, we will use I to stand for the current. So in our field, we usually use J to stand for the square root of -1. So keep in mind that sometimes I may write it as J, and sometimes I write it as I. So in physics textbook, they may still use I, but yeah, usually I'll use J to be negative of -1. In our field, all the textbooks use J, they never use I. Okay, but never mind, just a notation only. And yeah, maybe you would need to use MATLAB. In MATLAB, both I and J are initially used to stand for the square root of -1. So if you don't define a variable called I or J, then it stands for the imaginary number. So in MATLAB, try to avoid using I, J as the variable, because when you learn maybe C, or maybe when I was a high school student, I may learn the Pascal, then usually they will use for I equals 1 to 10, something like that. They may use IJK for the index to count. So for MATLAB, try to avoid using IJ, otherwise you may make mistake if you really need the imaginary number. Okay, so to go back to here, we have three cases. First case, positive, equal, negative. Actually here, for the final case, it is the most complicated one, but I will say this is the most useful one. So you should be able to handle all of the three cases. So let me start from the easiest one. So this is the first one, when we have distinct real roots. Distinct real root is very trivial, which means that we have roots S1 and S2. So they stand for a positive sign here or the negative sign here. So we have S1 and S2. And then in that sense, xc of t will be, this one, exponential to S1t, exponential to S1t. Because originally we know exponential to S of t should satisfy this one. S1 is a value, so when we put S1 there, this term should be a solution. This term should be a solution. And similarly, S2 is a solution to this equation. So which means that when we plug in S2 here, it should also be a solution. But why we have C1, C2 and add them together? The reason is linear. Linear means, suppose we call this one, let's say x1 of t. This is x2 of t. So when they are homogeneous solution, which means that f of x1 of t equals 0, and then f of x2 of t is also 0. So in that sense, suppose we have a linear property. So we should have a1 times fx. Maybe we can I can use a c1 x1 of t plus c2 f of x2 of t equals c1 times 0 plus c2 times 0, which should be 0. Okay, so this is the point here. So they both equal to 0. So even if I just multiply arbitrary real number here on the left side and right side, okay, 0 times anything are still 0. So here we have this big term to be 0. And then as much as we have a linear property, so we have f of c1 x1 of t plus c2 x2 of t equals 0. So which means that this is a more general homogeneous solution. So in that sense, when we have a second order homogeneous solution, and if the b squared or minus 4ac is larger than 0, then the homogeneous solution look like this: c1 times exponential to s1t plus c2 times exponential to s2t. So far you may be wonder what is c1 and c2. I would say c1, c2 are arbitrary number, which means that there are infinite many solution to this homogeneous solution. So sometimes we may get some so-called initial value, 初始值, then we may be able to determine what should be the unique solution to the differential equation. But before we have the initial value, or maybe sometimes we don't really have, we can only make it an unknown coefficient there, and then it means that it has infinite many homogeneous solution. Okay, so this is the first case, which is the easiest one. And then for the second case, if b squared minus 4ac is 0, so it has repeated real roots, because b squared minus 4ac is 0, or this term is 0. So both roots are equal to minus b over 2a. Okay, so in that sense, okay, if you still just follow the first rule, okay, you have s1 equal to s2. If you still write it like this, you will have c1 exponential to s1 of t plus c2 exponential to s2 of t. But here we have s1 equal to s2. So in this sense, this is s1, because s1 is equal to s2. So in that sense, this term is equal to this one. So it may be, it is something like this: c1 plus c2 exponential to s1t. So this is arbitrary number. When they add together, it is still an arbitrary number. So you may still write it as something like this. So you only have one solution. But for a second order homogeneous solution, you should have two solutions. So we have another one. So it's like this. Why we need to multiply by t? Okay, so if you don't want to know why, you just remember. if this has a repeated real roots, then c1 plus c2 times t. So it becomes a first order polynomial. And then let me try to explain why it is like this. Okay, so let me think. Yeah, let me see. Okay, so for example, later we will have this example: x double prime minus 10x prime plus 25x equals 0. And then we try to change second derivative to be square, and then first derivative to be s, and then the original function change it to 1. Okay, so it becomes this auxiliary equation, or characteristic equation. So you should get the roots to be this one. Okay, so why we have a t here? So let's see: x double prime minus 10x prime plus 25x equals 0. Okay, so far what we know is that x to the 5t is a solution. We don't know the second one. What is the second one? So let us try xc2 to be something like h of t times exponential to 5t. Okay, so let's try to multiply something, because it is a solution to this homogeneous solution. So it might be able to help us to find the remaining one. So let's try to multiply it by something rather than add it by something, because add is not useful because it's a linear solution. If it is added to 0, so it adds to something, then it doesn't change anything. So the only possibility is that it multiply by some other function to see whether it forms the solution to the homogeneous solution. So here we try to plug it to here. So of course we need to calculate the first derivative and second derivative. So for the first derivative, it is something like h prime of t, and then exponential to 5t, and then plus h of t times 5 exponential to 5t. So this is the product rule, because this is a function of t, this is a function of t. So we need to take the derivative of this one, multiply by this one, and then take the derivative of this one, multiply by the other one. So we have these two terms. And for x c2 double prime, it will become x double prime of t, and then exponential to 5t plus 2 h prime of t times 5 exponential to 5t, and then plus h of t, and then times 25 exponential to 5t. Okay, so we have the first derivative and the second derivative of this solution. Okay, so let's try to plug it in. So yeah, so first of all we have this term. So we have a h double prime of t, and then exponential to 5t, and then plus 2 times 5 is 10 h prime of t, and then exponential to 5t, and then plus 25 h of t exponential to 5t. Okay, so this is the first term, and then minus 10, and then multiply by this one. So this is h prime of t exponential to 5t, and then plus 5h of t exponential to 5t, and then plus 25h of t exponential to 5t equals 0. Okay, quite a lot of stuff. Okay, so here all the terms have exponential to 5t. Okay, so we feel very comfortable to divide exponential to 5t because it's never be 0. Okay, so we can just divide it out. Okay, so let's see whether we can have some cancellation. Okay, so here we have 25h of t, and then we have negative 10 times 5. So here we have negative 50h of t, and then we have still another 25. So this one, this one, this one, and this one cancel. Okay, so remaining one is this one, and also this one. Okay, so here this one and this one are still the same. Okay, so this is plus 10h prime and then minus 10h prime. Okay, so this is also cancelled. Okay, so all the terms are cancelled. Oh, this term, this term, this term, this term, this term, all the terms are cancelled except this one. So the final one, we get h double prime of t equals 0. Okay, the function, the second derivative of the function is a 0. So if we try to integrate both sides, h prime of t should be a constant. Let's say C2, a function, a constant. Okay, take the integration on both sides again, and then we will have h of t, and then we will have C2t plus C1. Okay, so this is that. So here we should have this xc2 of t to be like C2t plus C1 exponent. Oh, maybe we shouldn't call it C1, maybe we should call it, maybe just call it A or B, like A or AT plus B, so AT plus B. AT plus B, and then 5t, and then plus, this is the original one, should be like exponential to 5t, maybe we just call it C1, or maybe just C. Okay, because they are just unknown variable or undetermined variable, so we just name it as a different variable. Okay, so we can see this b times 5 exponential to 5t and this one are actually the same term, so it is like okay, so it is like at plus b plus c exponential to 5t. So here we can just call this one C1, call this one C2, and then it turns out to be C1 plus C2t, and then exponential to 5t. Because they are unknown variable, and then they add together. So they can be from negative infinity to infinity, and then when they add together, they still form one unknown variable. So we can just use a single one to stand for this. Two unknown variable adding together. Okay, so this is why when b squared minus 4ac is equal to 0, the homogeneous solution look like this form. So it's like this is the root. We still have this term. Rather than having a constant multiplying it, we have the first order term also. We have the first order term also. Okay, so this is the second case, a little bit more complicated than the previous one. And then for the second case, for the third case, b squared minus 4ac is negative, is smaller than 0. Then we should have complex conjugate roots. We can denote it as alpha plus or minus I beta or j beta. Okay, so yeah, this is the interesting thing. So yeah, of course it should be something like C1 exponential to or S1t plus C2 exponential to S2t. Here S1 is alpha plus I beta, and then S2 is alpha minus I beta. Okay, we don't really familiar with this thing. Okay, so actually this one is correct. You cannot say it's wrong. But here we will write it like this rather than this expression. Why we put like that? I'll let you know later. Soon. Okay, but yeah, if you don't want to know why, okay, I can say, okay, suppose we have the complex conjugate root. This is the real part, this is the imaginary part. Okay, so here we have exponential to alpha t. So for the real part, it goes to the exponential function. And for the imaginary part, this is the imaginary part. Okay, it goes to cosine and sine, and then multiply by unknown coefficients C1 and C2. So this is how the homogeneous for the case 3 of like. Okay, so let me try to explain why it is like this. Okay, so maybe I need to add one more page. So just now I mentioned x of t is actually C1, or maybe I just make it like a times exponential to S1t plus b times exponential to S2t. Here S1 is alpha plus I j beta t, and then plus b exponential alpha minus j beta t, like this. Okay, so here I need to mention an important equation called the Euler's formula. Euler's formula is like exponential to j theta is actually cosine of theta plus j times sine of theta. Okay, if you don't like j, you can just replace j by I. Yeah. But usually I rather like this. Okay, so here on the left side is exponential to j theta, and then on the right side cosine theta plus j times sine of theta. So it is something like what we will learn polar coordinate for the complex number. I think maybe you should have learned it in high school. So in high school, when you have a complex number like alpha plus j beta, you can also express it as the magnitude. So for the magnitude, it is like alpha square plus beta square, and then take the square root. Okay, the absolute value. So suppose z is like alpha plus j beta, then the absolute value of this complex number is like square root of alpha square plus beta square, and then just like this one. Okay, this is alpha beta. Okay, so this length is the absolute value of the complex number, and then of course it has an angle. Maybe call it phi or theta phi. So here we should have tangent of phi should be beta over alpha. Depends on which quadrant it is in. Okay, so we should have this one. So in this sense, you can just express this alpha plus j beta to be a complex number. So it is like the absolute value and then the angle. Actually, you can just write it as z and then exponential to j and then this angle. Okay, so this is the polar form. And for the polar form, okay, so you can just decompose it. Okay, this is the amplitude, and then multiply by cosine theta, because this side over this side is the cosine, this side over this side is the sine. So we have a cosine theta to be the real part, j sine theta to be the imaginary part. Okay, if you don't believe some other proof is like you can use a Taylor series to prove it. Like for example, exponential to x is like 1 plus x over 1 factorial plus x squared over 2 factorial plus dot 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 up to the infinity. And then you can also have cosine of theta to be 1 minus x squared over 2 factorial plus x to the 4th power over 4 factorial plus, minus x to the 6th power over 6 factorial, dot dot dot. And also sine of theta is x minus x cubed over 3 factorial plus x to the 5th power over 5 factorial minus x to the 7th power over 7 factorial up to the infinity. Okay, so these are the Taylor series for the exponential function, cosine function, and also the sine function. So if you just plug in x to be j theta to here, so here if you just change j theta, okay, you put x to be j theta, then you should have an expression. And then here we also this is x. This is x, not theta. On the right side is x. Okay, cosine of x is this one, sine of x is this one. Okay, so you just change x to theta, change to theta. Okay, so you can just plug in this one to there, and then you try to separate the odd term and the even term. Then you can find, okay, they are the same. Okay, so this is a not so rigorous proof. Okay, so here what I want to say is that try to believe this is correct. Okay, so if you believe this one is correct, let's try to go back to here. So we have a times this one and then b times this one. Okay, in this sense, we should have this one is actually exponential to alpha t plus j beta t. So if we have exponent add together, it is something like exponential to alpha t and then times exponential to j beta t. And then for that one, it is exponential to alpha t times exponential to minus j beta t. Okay, so in this sense, we have the common factor of exponential to alpha t. So we have exponential to alpha t and then a exponential to j beta t and then plus b exponential to negative j beta t. Okay, so here we have this term which is exactly the same as this one. So how come it will become like that for the remaining terms? So here we need to use the Euler's formula. Here we have this one, so we can write it as exponential to alpha t and then a times cosine of beta t and then plus j sine of beta t. And then for this one, we have plus b and then cosine of beta t, because cosine is an even function. So if it is negative beta t, it is nothing. Okay, and then for sine is an odd function. So if it is negative, here if it is negative, we should have a minus sign here, sine of beta t, like this. Okay, so we can just collect the same term. We will have exponential to alpha t, still the same, and then this one and this one, it becomes alpha a plus b and then cosine of beta t, and then we have plus j and then a minus b and then sine of beta t. Okay, so it more or less look like this. This is C1 cosine beta t, C2 sine of beta t, which is C1 cosine beta t, and then plus C2 sine of beta t. The reason is very simple, because the original differential equation is real. So we will expect the solution is also real. That's why we can just replace this constant to be a real number and consider this function to be also a real number. So we just change it to Z1, change this one to C2. Of course, it should satisfy something, which means that a plus b should be a real number, and then a minus b should be a purely imaginary number, which means that a should be the complex conjugate of b. A should be a complex conjugate of b. Like if it means a equals alpha plus j beta, b should be alpha minus j beta. Of course, this maybe I use another symbol. Maybe I should use gamma delta to distinguish from this alpha and beta. Okay, so this is a complex number, gamma plus j delta, and then b equals gamma minus j delta. Okay, if a plus b should be 2 gamma, okay, j delta and minus j delta will cancel, and then a minus b, gamma minus gamma, okay, it cancel, and then it becomes j2 delta, j2 delta. So if it's further multiplied by another j, so j squared will be -1, so it becomes another real number. Okay, so this is why if we want this coefficient to be real numbers, a and b should be the complex conjugate to each other. Okay, so here we explain why the third type will look like this. Why the third type is like this. So hopefully you can remember it. You don't necessarily need to derive it every time. So hopefully you can remember this is the first case When the delta is positive, we have this solution. When it is 0, we have this solution. When it is negative, we have the sinusoidal with the exponential multiply together as the solution. Okay, so this is the three types of the homogeneous equation. Or three types of solution for the homogeneous equation. Okay, so here we have some example. So we have a 2x double prime minus 5x prime minus 3x equals 0. Okay, so the first step is you try to change second derivative to be s squared, first derivative to be s, and then the original function change it to 1. So this is the only way you need to do. You don't really necessarily, you try to assume x to be exponential to s of t and then plug in and then cancel everything. The simple procedure is just change this one to s squared, change this one to s, change this one to 1, and then you will get it quickly. Okay, similar for this one. Second derivative, first derivative, and then original function, change it to s squared, s, and 1. You have s squared minus 10s and then plus 25. Also for this one, x double prime plus 4x prime plus 7x, you will get s squared and then plus 4s and then plus 7 equals 0. Okay, so this is the first step. Very easy. Just change second derivative to square, first derivative to s, original function to 1. Okay, so then we will try to solve. So this is what we should know in high school. So here, for this equation, the solution is negative 1/2 and 3. Both are real number and distinct. So the homogeneous solution is C1 times exponential to this number times t, so minus t over 2. And then S2 is 3. So we have C2 times exponential to 3t. So this is the first characteristic value, and then this is the second one. Okay, for the second case, we have this characteristic equation. The solution is 5 because it is actually s minus 5 quantity square. So the roots are 5 and it's repeated. So in this case, this is 5. So we have exponential to 5t, exponential to 5t, and then in the front, we have C1 plus C2 times t. This is a first order polynomial of time. Okay, so this is the second case, and for the third case, we have this characteristic equation, and then this is the solution. This is negative b over 2, negative b over 2. This is 4, so this is negative 2. And then b squared, b squared minus 4ac. B squared minus 4ac, 16 minus 4ac, 28. 28. 16 minus 28 is minus 12. Minus 12, which is 2 times square root of 3. Okay, you have 16 minus 28, so which is square root of negative 12. So it is negative 2 square root of 3i. Okay, and then of course you should divide by 2a. So for the 2a is 2, so cancel with these 2. We have a square root of 3i, negative square root of 3i. So the real part is negative 2 and the imaginary part is square root of 3. So in this sense, real part, put it here, exponential to negative 2t. Imaginary part, square root of 3. So cosine of square root of 3t, sine of square root of 3t, and then multiply by C1 and C2, and then add them together. Okay, so this is the 3 cases for the homogeneous solution. Okay, so here we finished the first step. And of course, the third step will also be easy because we just add them together. So we have nothing to do. But for the second step, it might be more complicated for you. But yeah, maybe we don't have enough time to talk about it. So just let you know, and we have some specific types of function for the g of t we may be able to solve. So like a polynomial, exponential function, sinusoidal function, or maybe we just pick 2 of them or 3 of them together to multiply together. Then we can still know the function. You may ask, oh, how about other functions? Usually in engineering problem, we seldom face function other than this. Yeah, and if you really need it, you probably need to know what is Fourier transform or Laplace transform. Then you may be able to solve some other function for g of t. But before you learn Fourier transform and Laplace transform, knowing all these types is already quite sufficient. Okay, so let's stop here today, and I'll see you next week.